Hello guys, good evening. Can you hear me?
Yes, sir.
Okay. One minute, just 1 minute. Yes. So today, guys, we are going to start a new chapter, coordination compound. Okay. From inorganic chemistry, a very important topic. You're going to have one definite question from this. Okay. There are so many types, different types of questions forms from this chapter. This chapter requires a bit of information of chemical bonding, valence bond theory, hybridization, plus concepts of isomerism is also applicable here, right? We'll see how the coordination compound shows isomerism, geometrical and optical. So all those things are important. In fact, on isomerism, optical isomerism, in fact, stereoisomerism, they ask questions every year in the exam. Okay. Is this fine, whiteboard, or do you want me to go for the blackboard?
Black one, sir.
Black. Okay. So okay. Just a second. Just take some water and we'll start. Okay. So coordination compound. See, coordination compound, we also call this as complex compound. Coordination compound or complex compound. It differs from the normal compound in many aspects. We'll discuss all those things one by one. Okay, but first of all, we'll see what is the use of this compound and why we are studying it. Obviously, they ask questions in the exam, but what is the use we have in day-to-day life? Okay, you must have heard about chlorophyll, right? Chlorophyll. Chlorophyll is the complex of magnesium, right? It is a complex compound of magnesium. Okay. Hemoglobin, right? It is also a complex compound, but it is a complex of iron. So with these two examples, you must have understood this, that how this particular type of compounds, that is coordination compound, is important for our day-to-day life or for human being, right? That's one thing, okay? This kind of, this coordination compound is mainly formed by, mainly formed by transition element. Transition metal. Why? We'll discuss this generally, right? Coordination compound, like the basic difference between this and the normal compound we have, that we'll try to understand. Let us take two examples here. One, I am taking NaCl, which is a normal compound, simple compound in fact. It is a simple compound. And other one I'm taking, that is K4Fe CN6. It is a complex compound or coordination compound. Complex compound or coordination compound. Okay. In NaCl, what happens, if you dissolve this in water, if you put this into water, right, it dissociates into, in H2O, it dissociates into its ions, that is Na plus aqueous and Cl minus aqueous. Cl minus aqueous. So it completely converts into its ions. Okay. Here, if you put this into water, then this also dissociates. It dissociates into 4K plus Fe CN6 4 minus. Okay. So for this one, this part, the complex part here, the portion here in this square bracket, this part we call it as complex part. And this makes the entire difference in the two examples we have. It is a complex part, right? So complex part, when you dissolve this complex compound into water, this complex part still maintains its identity here. It won't dissociate into water, right? So this, what we can say, this retains its identity in the solution. But this won't happen in case of simple compound. It completely converts into this. There is no retention in the properties. This molecule converts into ions, but here we have the retention. So this is the basic difference between complex compound and the simple compound. Okay, that the complex compound retains its identity in the solution itself. Okay, this part won't dissociate. This is one major difference we have. The another difference is what? In complex compound, we have two types of valencies. Okay, primary and secondary valency. That is also a different, kind of concept we have here. All these things, we'll discuss one by one. Okay, I'm just trying to compare the two, compounds here, complex and simple compound, so that you can understand what is the, difference we have here in these compounds. Basic understanding you must have. Right? So we'll discuss all these things in detail. And like I said, this chapter, if you want to understand, you must have the understanding of chemical bonding properly. Because here also, you are going to have valence bond theory. Okay? Overlapping of orbital, hybridization, everything's are there. Okay? And this thing that I said, it is, it is very, very important. as important as the isomerism in coordination compound we have. Okay, so one by one we'll discuss all this. So before going into this, that what is a complex compound, what are terms associated into it. So basically, there are different terms we use for coordination compound. But before going into those terms, let us first understand the classification of compound and where these complex compounds are placed in the classification of compounds. Okay, so next page you see heading is classification of compounds. Classification of compounds. Compounds mainly are classified into two categories, first of all. One is additional compound. Additional compound also known as molecular compound. And the other one is simple compound. Simple compounds are simple molecules. We have examples here. NaCl, NaOH, MgCl2, HCl, many things, okay? HCl, etc. All these are simple compounds. Further, this additional or molecular compounds again classified into two categories. In the two categories, first one is double salt, and the second one is coordination compound. Coordination compound. Right? So this is our topic today, coordination compound. It comes under additional or molecular compound. Okay. So one by one, we'll see the definition of additional compound, then double salt, and then coordination compound. Okay. So all of you write down the first thing here, that is additional or addition or molecular compounds. Write down. When two or more more simple, stable compounds joins together, they forms additional or molecular compounds. Example is, we have KCl dot MgCl2 dot 6H2, carnallite, FeSO4 dot NH4 2SO4 dot 6H2. This compound we call it as Morse salt. The name of the compound is and this compound is carnallite. Okay, these are additional compounds because KCl, MgCl2, H2O, these are the simple compounds. When they join together, they forms additional compound. Now we know this additional compound is further classified into two categories, double salt and coordination compound. Let us write down the definition of double salt first. This chapter, guys, is very conceptual, logical chapter, right? It's not like the usual inorganic chemistry where you have to mug up things, right, randomly. It's not like that. I would say 80-85% things are there to understand, right? If you understand the concept, you can do it easily. But yes, little bit of information is required. So that comes under 10 to 15%. That few things, if you memorize, if you know that, you can do it easily. Okay. So what all things are there? That's not very difficult to memorize. It's very basic. When you read some any books, if you go through once, you will understand those things, and it will be there in your mind. Okay? Few things you know already. Okay, we'll discuss that, and you'll understand this. Okay. So double salts are what? These are the compounds. These are the compounds which are stable in solid state. In solid state, but when dissolved in water, it breaks down into individual constituents ion. For example, you see, if you take the example of carnallite, okay, KCl dot MgCl2 dot 6H2. If you dissolve this in water, right, it converts into K plus Mg2 plus 3Cl minus plus H2O will be H2O only because the solvent is water itself. Right? So this is the meaning of double salt. Could you tell me the N factor of this compound? Not required here for this particular chapter, but yes, randomly I'm asking. What is the N factor for carnallite? Yes. Yes, it's 3. How do we find out N factor for a salt? You can count total positive
total number of cations or anions.
Anyone, right? Either total positive charge or negative charge. Here the positive charge is 3 and negative is also 3, and hence it is the answer. Yes, correct. That is a double salt. Now the important one is we have coordination compound. Have you done this chapter in school?
Yes, sir.
Okay. Write down. These are the compounds in which some of the constituents ions or molecules loses their identity loses their identity when dissolved in aqueous solution. When dissolved in aqueous solution, but do not break up completely into ions. Okay, do not break up completely into ions. Then I'll repeat it again. These are the compounds in which some of the constituents, ions or molecules, loses their identity when dissolved in aqueous solution, but do not break up completely into its individual constituents, ions. Okay, complete breakup is not there, right? Like example I given you, K4FeCN6. FeCN6 does not dissociate into its ions, right? Potassium loses its identity completely, but not the complex part. That is FeCN6 4 minus. Okay, so here you see some more examples. The first example I have already given you. That is K4FeCN6, and this convert into 4K plus FeCN6 4 minus. Okay, this one does not lose its identity. Whatever it is written in the square bracket, that is the complex part we have written in the square bracket. If you talk about this CONH3, 6 and Cl3, this converts into CO. CO is cobalt here, right? CO NH3 6 3 plus 3 Cl minus. This compound, the complex part is the negative ion is the complex part. So we call it as complex anion. Complex anion, because anion is complex here. This one is complex cation, this particular compound. Complex cation. Okay. Similarly, we can have complex anion and complex cation, both possible. Because both part, cation and anion, could be complex also. Okay. Now, before going into this, let us try and understand what are the different terms we have that we'll use in this chapter. Okay. The terms involved, we'll take one example, and with respect to that only we'll discuss. Suppose the simplest one I'm taking K4FeCN6, and this is present in the square bracket. So first of all, this complex part which is written in the square bracket, this we call it as coordination sphere. Coordination sphere. Okay, this one is the central metal atom. Central metal atom. That is, in short, we write it as CMA, central metal atom. We use this abbreviation for this, central metal. Apart from central metal atom, whatever is written in the square bracket, we call it as ligands. What are ligands? Okay, K plus is what? this, like apart from this square bracket, this coordination sphere, the other part we call it as ionization sphere. Ionization sphere. Okay, or we also call it as counter ion. Ionization sphere or counter ion, both are same thing. Okay, so this one is complex anion because the negative part is complex. Ligands are what? Ligands are electron pair donors. Electron pair donors. It donates electron pair, not electron, but electron pair to the central metal atom. That is ion here in this case. Copy this down. Okay, done. So these are the terms we are going to use in this chapter: ligands, coordination sphere, central metal atoms, in short, CMA, and other things. Terminology, right? So first we'll see what are ligands. Next page. Write down ligands and its classification. Ligands and its classification. So write down write down ligands are the atoms, ions, or molecules which donates electron pair to the central metal atom or ion. Central metal atom or ion. Okay, it gives a pair of electron, right? Electron pair it is. This one is electron pair. 1 second, just 1 second. Yeah. So ligands are electron pair donors. Hence the bond between metal atom and ligands, if you see, it is a coordinate bond. Right? So metal atoms are attached with a coordinate bond with ligands. Okay. Yeah. Now, since ligands are electron pair donors and metals are electron pair acceptors. Hence, we can say that ligands behaves as the Lewis base since it donates electron pair, and metal atom accepts electron pair. Hence, metal atoms are Lewis acid, behaving as a Lewis acid in the complex. Okay. So, there's 2-3 things about ligands you should know. First of all, it behaves as Lewis base electron pair donors, right? Next thing, it can be neutral, positively charged, or negatively charged. Any 3 things possible. Negatively charged, positively charged, or negatively charged. Okay. They have different denticity. What is denticity? Like how many pair of electrons a ligand can donate, that becomes the denticity of that ligand. In detail, we'll discuss this. Okay. Then it attached with or in short, I'll write down coordinate bond with metal or central metal atom CMA, right? Central metal atom CMA. If we talk about the classification of ligand, we have 2 types of classification. Two types of classification. Okay. Another thing, that ligands donates electron to the metal. So metal must have the capacity to accept electron, and for that we need vacant orbital in the metal atom, right? And that is the reason mostly transition metal, because transition metal has vacant d orbital, hence mostly transition metals can easily form complex compound. Okay, can easily form complex compound. Ligands are what? Ligands are electron pair donors. All those molecules which has available electron pair, like lone pair or pi electron cloud, like in benzene, all those molecules can behave as a ligand. Okay, so must have electron pair present on it. Okay, so this is Lewis base we have done. One point here, you write down one note, that central metal atom CMA accepts a pair of electron from the ligand hence behaves as Lewis acid. Central metal atom behaves as Lewis acid. Right? Accepts electron pair and hence behaves as Lewis acid. Finish. Now the classification of ligand, we have 2 types of classification. One is classification based on charge. All these things I'm discussing here for ligands only, right? So classification based on charge. Based on charge. So three types of, obviously ligands we have. One is neutral, other one is positively charged, and other one is negatively charged. So neutral, then negatively charged ligand, and the third one is positively charged ligand. Positively charged ligand. Okay. Neutral ligands, you should know the examples. Okay, it's important. I'll tell you why and how. Example. Neutral ligands, we have many examples. We have H2O, there's no charge. NH3, we have lone pair of nitrogen, no charge. We have NO, nitrosyl group, no charge. Benzene, we can take pi electron cloud, no charge. Okay. And we have carbon monoxide also, no charge. Okay. All these are neutral. Yes, that also you can write ethylene diamine. That is also a neutral, this thing, neutral ligand, ethylene diamine. Okay, we'll discuss those examples also. Negatively charged ligands are, we have halide ion, nitrite ion, sulfate ion, okay, cyanide ion, hydroxide ion, etc. Positively charged ligands are very few, right? NH2, NH3. NH2, NH3, we have positive charge. Donor atom is this nitrogen, electron pair chloride. And we also have nitrosonium ion, NO+. Nitrosonium, NiUm ion, that is NO+. Copy this. Nitrosonium, nitronium, yes, that is also fine. Okay. Now, why charge are important here? Because when you calculate the oxidation state of metal, so for that you need charge on the ligand. Okay, we'll have the nomenclature of coordination compounds. So, right, the rules are very similar. With the nomenclature we have done very similar rules, but to find out the oxidation state of metal, because that to mention in the name of the compound, right? So to mention the oxidation state, we need to find out it, and for that we require the charge on ligand. And in the question, the charge on ligand is not mentioned. That you should know. Okay, that's why this charge is important, very important. Okay, now The next classification of this thing, ligands are based on it's denticity. Write down next classification based on denticity. Classification based on denticity. So first of all, we need to understand what is denticity of a ligand. So write down the definition of denticity. Tell me, what is denticity? Anybody?
The number of atoms which can donate electron pair.
The number of electron pair.
The number of atoms which can donate electron pair in that ligand.
A number of atoms which can donate electron pair, that is a denticity. Okay. Anything else? Number of lone pairs that can be donated to the CMA. Achha. Number of atoms attached to the central metal atom. Yeah, that's correct. Number of atoms attached to the central metal atom is correct. Yes, right, Sana. Number of electron pair that is donated, that is also correct, Pratham. Siddharth, when you say number of lone pairs that can be donated to CMA, that is not the correct definition. There's a thin line, the difference between the two. You will understand this. Let me discuss this, you'll get it. Okay? Yes, number of ligands binded to the central atom. Number of ligands binded to certain extent, it's correct. Right? Basically, if you say the number of atoms of ligand that is attached to the central metal atom is the denticity of that ligand. Okay. If you say it is a number of electron pairs that can be donated by a ligand to the central metal atom, that is not correct, because the denticity can be anything 4, 5, 6, but it is not necessary that a ligand with denticity 6 will show 6 coordination number in the complex always. Right? Denticity, the maximum capacity is 6, but it can show 5 also or 4 also. That's why we always take the number of atoms of ligand which is attached to the central metal atom in the complex. Okay. A thin difference, like I said, a thin line we have between the two. You'll get it like once I discuss it. So first of all, you write down what is denticity. Definition. It is a number of electron pair accepted by a central metal atom or ion number of electron pair accepted by a central metal atom or ion from a particular ligand known as the denticity of that ligand in that complex. I'm repeating myself. The number of electron pairs accepted by a central metal atom or ion from a particular ligand is known as the denticity of that ligand in that complex. Okay. Again, I am repeating this. ligand, can donate 4, 5, 6, any number of any pair of electron, but it is not necessary that a tridentate ligand or pentadentate ligand will always have denticity 5 or 3 in the complex. It can be less than that also. Depends upon the structure and oxidation state of the metal. Okay, so denticity is the number of electron pair accepted by a central metal atom from which a particular ligand is known as the denticity of that ligand. Or in the other way, you can say in the bonding state, you just need to check the number of atoms of ligand that is attached to the central metal. That is the denticity. Fine, anyways. So denticity, based on denticity, the ligands are classified into 6 categories. Okay, into 6 categories, and you should know here the examples of each category plus the structure, because a structure is required. Sometimes they'll ask questions on the donor atoms. Which one is the donor atom in a given ligand, right? For that, you should know the structures. The first classification, like I said, 6 classifications there. The first one is monodentate ligand. Monodentate ligands are those ligands whose denticity is 1, right? Denticity is 1. The example we have, okay, the example of monodentate ligand, just write down denticity 1 and then write down example. We have H2O, oxygen is the donor atom, NH3, nitrogen is the donor atom, Cn minus, so monodentate ligand. Then we have X minus, monodentate ligand, CO, NO2 minus, OH minus, and NO. See, NO here, it's important. Okay, we'll discuss this later. I'm just mentioning it here. NO is we say it is very, the property of this, whether it is, obviously it is monodentate, but whether it is, neutral or positively charged, it depends upon the complex. Okay, so it behaves in a different way in the, complex. Important also, we'll discuss this later, because when you see the complex, you see here, if I write down this example, K4FeCN6, here the charge on cyanide is -1. Once you know this, Cn minus is the charge, right? But in the complex, the charge is not mentioned, right? So, we have NO is a ligand, we have NO plus is the another ligand, right? But for both, it is NO only that is mentioned in the question, in the complex. So whether this NO is neutral or positively charged, that is a bit, confusing to understand in the question. Based on this, they have asked question in JE. Okay, so we'll discuss this. So please take care of this NO thing, nitrosyl, whenever it comes into the paper, whether it is neutral or positively charged, you have to take care of that. Okay, we'll discuss this when we, go a bit ahead in this particular chapter. But I've just given you this information that NO, you have to be a bit careful in case of NO, as far as the charge on the ligand is concerned. Okay. So second type of classification, we have monodentate, then we have bidentate. Bi or didentate, both are same thing. Bi or didentate, whose denticity is 2. Bi or didentate, whose denticity is 2. The example we have ethylene diamine. Ethylene diamine. Okay. In short, we write it as EN, and the structure is CH2CH2. N, N, H, H, and this is the donor atom, 2 nitrogen. 2 nitrogen are the donor atom. Denticity is 2. Bidentate or didentate ligand. Done. Next. Next one is oxalate. Oxalate is C2O4 2 minus, and its structure is CO minus. Then we have double bond O this side, double bond O this side. Both oxygen are the donor atoms here. Oxalate ion. OX is the symbol we have. Next one is glycinate. These are the donor atoms, nitrogen and oxygen. Glycinate, GLY is the symbol. The other one is carbonate. You all know the structure of carbonate ion. CO3 2 minus. Okay. C double bond O, O, O negative, negative, and this is the donor atom. Copy this down. Okay. The next example is dimethyl glyoxine. DMG. Structure is C double bond N, O minus, C double bond N, OH, CH3, and CH3, and CH3. The donor atoms are these 2 nitrogen atoms are the donor atoms. Another one is dipyridine. That is DIPY. Dipyridyl is this. Present in the ring, the nitrogen. Both nitrogen atoms are the donor atoms. Oxygen can also donate, But since it is more electronegative, so nitrogen donor atom here.
Okay, sir.
OH also you can write here, glyoxine. Okay, see that?
Yes, sir.
Yeah, dipyridyl is this. Next one is tridentate ligand. Whose denticity is 3. The examples are diethylene triamine, diethylene triamine. Easily you can draw the structure. See, CH2 whole twice is diethylene. Triamine is this. And one NH2 here, one NH2 here. Diethylene and triamine, one hydrogen we have with this nitrogen. Right? This is donor atom, this is donor atom, and this is donor atom. There are 3 donor atoms here. And the symbol for this one is diene. Next is terpyridine. Terpyridine, T-E-R-P-Y symbol is. And the structure here is one, two, and 3 donor atoms. Terpyridine. Tetradentate. Copy this down. I'll go to the next page. Then next write down tetradentate, then we have penta, and then we have hexa. 3 more. Tetradentate ligand, denticity is 4. Okay, and the first one is nitriloacetate ion. For example, we have N, the structure is N. We have CH2, C double bond O, O minus. Same thing, CH2, C, O, O minus. Next one we have CH2, C double bond O, O minus. And all these oxygen atoms are donor atoms. Okay. Fourth atom is this nitrogen. 4 donor atoms we have here. Another example is triethylene. Triethylene tetraamine. Triethylene tetraamine is this. 3 ethylene group we have. So one is this. Tetraamine is this one, NH. Here also we have NH, and this is attached to CH2 whole twice. Here also we have CH2 whole twice. 1, 2, 3 ethylene group, 2 amine group, and 2 more we have here, NH2. So triethylene tetraamine. Donor atoms are the 4 nitrogen atoms. 1, 2, 3, and 4. 4 nitrogen atoms are the donor atoms. Done? Okay. Tetradentate we are done. Next one is pentadentate. Pentadentate ligand. Pentadentate ligand, denticity is 5. Example we have EDTA 3 minus. What is this? Ethylene diamine triacetate. Triacetate ion. So ethylene diamine, right? So ethylene is this CH2 whole twice. Diamine is 2 nitrogen on both sides of it. Diamine, but diamine triacetate we have. Okay, so diamine triacetate means one side we have CH2, CO minus double bond O. Here also we have CH2, CO minus double bond O. Here also we have CH2, CO minus double bond O, and 1 hydrogen. So donor atoms here you see, the donor atoms are 1, then we have 2, then we have 3, and then we have 4, and then we have 5, 1, 2, 3, 4, 5. Pentadentate ligand. 2 nitrogen and 3 oxygen atoms are the donor atoms. Hexadentate ligand, the last one. Hexadentate ligand. Just a second. Denticity is 6. And the example is EDTA 4 minus. Ethylene diamine tetraacetate ion. Could you draw the structure of it? Ethylene diamine tetraacetate ion. What is the structure? You can remove that fourth hydrogen or nitrogen atom, add one more acetate ion here. Means this hydrogen you remove and add CH2COO minus, oxygen is the donor atom. Yeah, that is the structure of ligands. The structure I have given because donor atoms you must know. Done?
Sir, does it matter where the donor atoms are placed in the molecule?
Sorry, what?
So does it matter where the donor atoms are placed in the molecule? Like if they're
No,
far
no.
from each other or something?
No, distance and all, there is no effect.
Okay, sir.
Distance, because it is arranged in the space, three-dimensional space. And because of that only, it can show stereoisomerism, which we'll discuss later.
Okay, sir.
Right, so when it donates electron to the metal atom, then it arranges itself in such a way so that that donation and then bonding is possible.
Yes, sir.
Yeah. So these are the few things. Now the thing is, why these coordination compounds are forming, and why metals are accepting electron from the this thing, what we say, ligands. Okay, why metals are like in normal compounds we say that metal like atoms forms bond to gain octet, to gain stability. This kind of theory is there, right? So here also metals accept electron from the ligands in order to gain the next higher noble gas configuration. Okay, suppose you have one example of same thing, K4 efficiencies. Atomic number of ion is 26. So what is the next higher noble gas configuration? What is the atomic number of that?
That is
Hello? Hello?
36.
26, and the next higher, the noble gas is 36, that is krypton, correct? So metal that takes electron, suppose iron is the metal, Fe, has 26 electron, and it takes electron from the ligand, and it has tendency to make it 36, the total number of electrons, the net number of electrons, right? That is the tendency of the metal atom. This kind of behavior we observe in some compounds, but it is not like it is always there, right? It is something like the bonding theory that we discussed in chemical bonding. There are different theories, right? We have valence bond theory, we have VSEPR theory for structures and all, and then we have molecular orbital theory. Hybridization is another kind of theory of bonding. No, so there are different compounds which follows different kinds of bonding theory. So here also we have different theories. We have valence bond theory, we have here also. We have Werner's coordination theory, we have here also. Apart from that, we have this rule also, that all there are metals which has tendency to accept electron from ligands and gains the next higher noble gas configuration. But it is not true for all the metal atoms. Okay. So this rule, we call it as Sidgwick EAN rule. Okay, effective atomic number rule. Okay, so what is this? Let's see. So first of all, write down the heading, effective atomic number. effective atomic number. In short, we write EAN. We also call it as Sidgwick. The name of the scientist is this. EAN rule. Sidgwick EAN rule. This rule is, it is observed to be true in case of metal carbonyl compound. Means metal and carbonyl compound is there, CO group is there, then the rule is correct mostly. And in some book it is written also, Sidgwick EAN rule is valid only when the metal has carbonyl ligands. CO is the ligand over there. Okay, so what is the effective atomic number? The effective atomic number for any metal in the bonding state, if you try to find out, then what you'll do? It's a very basic thing you can understand easily, that effective atomic number means net number of electrons you are trying to find out after the bonding, right? That would be equals to atomic number, which was initially there, right? This is atomic number. And in that way, it loses some electrons also. So we'll write oxidation state minus oxidation state with the charge, with the sign actually. Means if it is +3, then we'll write +3 here. -3, we'll write -3 here. Oxidation state with the sign. Plus the number of electron just a second. Okay, so it is the number of electrons gained from ligands. So basically, if you think on this particular equation, plus and minus, it is the total number of electrons we are trying to find out on a metal in the bonding state. Okay. So for that, what all things you need to know that you see here. Suppose the first example I am taking, K4FeCN6. We need to find out the effective atomic number for this complex. That is the question. Effective atomic number for this complex. Okay. So we'll find out.
Excuse me, sir.
Yeah.
Sir, what is that on the right, sir? Number of electrons gained from the ligands, right?
I should write here ligand.
Okay.
Okay. So K4FeCN6. So if you try to find out the effective atomic number for this thing, iron here, what we'll do with this formula, or if you do not know this formula, effective atomic number means the total number of electron the metal has in this bonding state. So what we'll do, we'll write down the atomic number first of all 26, because iron has 26 electrons. And if you try to find out the oxidation state, what is the oxidation state of iron here? Could you tell me?
+2.
+2, right? Means it has lost +2 electron, right? So minus +2 oxidation state plus how many electrons it accepts from the ligand? There are 6 ligands and one ligand can give 2 electrons. So 6 into 2, the number of electrons. And when you solve this, you'll get 26 plus 12, that is 38. 38 minus 2 is 36. Got it? 36 is the atomic number of krypton. So next, higher noble gas configuration. Could you calculate this for CrCO6? CrCO6. Calculate effective atomic number here. And the next one is FeCO5. FeCO5. CO here is the carbonyl ligand. Okay, don't get confused with cobalt. CO5. If CO is not the central metal atom, it is ligand, right? If it is not ligand, then it is cobalt. Calculate the effective atomic number for this too. What are you getting? EAN value here and EAN value here. $38 you are getting in both. I don't think so, Aditya. $36 in both. Okay, the first thing you need to find out. Yes, the first thing you need to find out is the oxidation state of the metal. All these are neutral ligands. 0 is the charge. Right? 0 is the charge. So it has 26 plus 10, 36. 24 plus 12, 36. So for this one, the value is 24 minus 0 plus 6 into 2. And this is equals to 36. For this one is 26 minus 0 plus 5 into 2. And this becomes 36 electrons. Okay, 36 electrons both complex has. Hence, it follows Sidgwick EAN rule, right? But for some examples like this one, Cu NH3 whole 4, then SO4 we have here. For this one, you find out the effective atomic number. Tell me. You are getting 35, right? So effective atomic number, you see NH3 is neutral ligand, sulfate is -2. So on this complex, we have +2 charge, and hence the oxidation state of copper is +2. Is it right? So the value of EAN, yeah, 35 is correct, is copper is 29, oxidation state is +2, plus 4 into 2, and this becomes 4 into 2, and this becomes 30. Okay, so you see the effective atomic number for this one is 35, it is not 36. That's why the Sidgwick EAN rule is not valid for all the complex. Okay, but we have few application of it which is very important. We'll discuss that. One more thing you try to understand, we are finding out the oxidation state of metal, and for that you should know what is the charge on the complex and ligands that is there, because without that idea, the charge on ligands or this thing, the charge on ligands, you are not be able to find out the oxidation state of the metal. And you must have seen that in nomenclature of coordination compound also, we have to mention the oxidation state of the metal just after the name of it. That's why the charge on ligand you must know. Okay, so this is one thing. Now you see this example. What is the effective atomic number? One question I'll show you here. See this. The question is, why MnCO5 the complex we have, exists in its dimer form, that is Mn2CO10. Tell me this. Basically, MnCO5 does not exist, Mn2CO10 exists. Why MnCO5 exists in its dimer form?
So because MnCO5 will have 35 EAN, so when it forms dimer, it will form a bond between Mn and Mn, so that will make it 36.
MnCO5, you said it has 35 EAN value, right?
Yes, sir.
So what happens in the dimer form?
So when a bond is formed between two manganese atoms, EAN will increase by 1 because electron is shared. So it will become 36, which is krypton EAN.
Okay. That's right. No, chelation is not there. Chelation is a ring complex it forms. Right. Wait. See, if you find out for MnCO5, you must have done this, the effective atomic number for MnCO5, and we are getting 35 here. EAN value is 35. But if I ask you to find out the effective atomic number for Mn2CO10, what is this number? What is this number? Mn2CO10? For each manganese atom? Yes, tell me guys. Did you calculate this, Anjali?
So?
You got it, 36?
Yes, sir.
How?
So because 35 is in the MnCO5 form, and in the dimer form, since there's a bond between the two manganese atoms, it's going to become 36. You add 1 electron.
Yeah, correct. So basically, if you look at the rough structure, if I draw here, we have a manganese-manganese bond, right? Mn bond. And 5 CO is already there, 1, 2, 3, 4, and 5. All these are CO, right? CO, 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 and CO, and CO. Okay, so this contains, like, you leave this electron here, this one you let it be. Apart from this electron, an entire thing has 35 plus 1 more electron we have here. So 36 electron this manganese has. And similarly, we have 36 on this manganese also. 1, 2, 3, 4, and 5. Right? CO, 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 and CO. Okay. So if you count the number of electrons, manganese has 25 plus 10, 35 plus 1 electron of this manganese in this form. So both manganese atom has 36 electron, which has noble gas configuration, and hence MnCO5 dimerize into Mn2CO10, which is the more stable form. Okay. Okay. One note you write down here. Metal or metal ion. Metal or metal ion in a complex. Metal or metal ion in a complex tends to acquire metal or metal ion in a complex tends to acquire noble gas configuration by accepting electron from the ligands from ligands. However, this rule fails in many cases. And works best for metals in low oxidation state. One second. Low oxidation state and with metal carbonyl compound. Low oxidation state, but low oxidation state again they don't define. So it is basically works well for metal carbonyl compound. Okay. Now application of this rule is what? That we can understand, we can find out the coordination number first of all, and we can also find out the oxidizing or reducing behavior of a complex. These are the two applications of it. And they ask question on this also. Write down the heading next, application of the first one is to find coordination number. Coordination number we haven't done now. I'll tell you what is coordination number. To find coordination number, we haven't done few things. Okay, I'll do it. Wait. Okay. To find out the coordination number. Coordination number is what? It is the number of, the same thing like we did denticity. Coordination number is also the number of atoms of ligands that are directly attached to the, central metal atom. So we can find out coordination number with the help of Sidgwick EAN rule. It's very simple. I'll show you how. Suppose one, a complex is given, and the complex is this. FeCOX. And they'll ask us to find out the coordination number. Means how many atoms of this ligand is attached to this ion. So we'll find out EAN. And we know according to this rule, the effective atomic number should be equals to 36. That's what we need to do. So iron already has 26 electron, and there is no charge on, the metal because it is 0, it is neutral ligand. Plus, suppose its coordination number is, x, I am assuming, x into 2 is equals to 36, and you can solve this equation for x. X value you'll get 5 here, hence the coordination number is 5. 5 ligands are required here, carbonyl ligands, FCO6. Could you find out for Ni, what is the coordination number for this one? NiCOX. Is it 4? Yeah. X value is 4 we are getting when you solve this. Ni is 28. Okay. So coordination number is 4. This is the first application. Second one, we can find out oxidizing and reducing behavior. And reducing behavior. Let's see this example. We have this MnCO6 and we have vanadium CO6. If you find out EAN for this, manganese is 25 minus 0 plus 6 into 2. So we are getting 37 electrons, more than 36. Okay, that's why what happens, this MnCO6 has tendency to, MnCO6 has tendency to lose electron and converts into MnCO6 plus, what did I write? MnCO6 plus 1 electron. So this one has 37 electron. So this one will have 36 electron, and hence this is behaving as, it is getting oxidized. It is behaving as a reducing agent. Similarly, could you find out for this one, BCO6, what behavior is this?
Sir, what is vanadium atomic number?
Scandium, titanium, vanadium. 21, 22, 23. 23 is atomic number. Done. How many electrons this has EAN value?
35.
35, right? So it has tendency to accept one electron, right? So this accepts one, just a second. This has tendency to accept one electron, this plus one electron, and this converts into VCO 6 minus. So it is getting reduced. This is behaving as oxidizing agent. Right. So we can find out the oxidizing reducing property and the coordination number of the ligand. Okay. So apart from this, we have few more different types of ligand. We have seen ligands based on their denticity, that is monodentate, didentate, bidentate, tri, tetra, penta, hexa. We have seen that. Few more we have. You see this another type of ligand we call it flexidentate ligand. Flexidentate ligand. Write down the definition of this. Write down. A polydentate ligand. Again, one more thing. Polydentate ligands are those ligands whose denticity is 2 or more. Right? So except monodentate ligand, all ligands you can consider as polydentate ligand. Right? Except monodentate, all ligands are considered as polydentate ligand. Correct? So write down a polydentate ligand is found to have different denticity Hello? Hello, am I audible?
Yes, sir.
Yes, sir.
Yes.
Yeah. So what did you write? A polydentate ligand is found to have different denticity in different compound and hence they called flexidentate ligand. Their denticity is flexible depending upon the metal oxidation number plus structures and other things, and what other ligands are present. Okay, I'll show you some examples here. This means what? Next line write down. It is not necessary. It is not necessary that all donor atoms present in polydentate ligands right? All donor atoms present in polydentate ligands forms a bond with the central metal atoms. Forms a bond with central metal atoms or ions. This means what? If you talk about EDTA 4-, what is the denticity for EDTA 4-?
6.
Denticity is 6, right? But it is not necessary that in all compounds, its denticity is 6 only. It can be 5, 4, anything, depending upon the molecule, right? Means what? If the denticity is 2 or more, then it can change its denticity depending upon the requirement of the complex. And hence, it is known as flexidentate ligand. I'll show you this example, you see, since we have already understood now Sidgwick EAN rule. So I want you to, find out the denticity of carbonyl ligand, that is CO, in this complex. CONH3 CO3. Just a second. CO3 carbonate ligand it is, and we have Br outside of it. Another one example is CO NH3 CO3 carbonate, and then we have Br. Tell me the denticity of carbonate in this compound and in this compound. These two ligands and its denticity. Flexidentate is the properties of polydentate ligands. All polydentate ligands can show different denticity in different compounds. So yes, it is for all polydentate ligands. First one you are getting 2, Sahana.
So, but doesn't it depend upon the oxidation number of the
That is
metal?
what I'm asking you. You have to calculate that oxidation number, and then the other things. Yes. Okay, I got the answer. We'll see. We'll discuss it, Sahana. Just a second. So you need to find out the oxidation number of the metal, and then you see what is its requirement, means how many electrons it requires to gain the next higher noble gas configuration. Accordingly, you should think of that how many atoms are attached with the central metal atom. What is 0 there, Pratham? What is the oxidation state of cobalt in both molecules? Tell me.
3, sir.
Pratham, tell me the oxidation state.
Sir, 3.
+3 in both.
So the first one is +3.
And the second one? Second one is also
Same,
+3.
sir, yeah.
NH3 is neutral only, right?
Yes,
That's why you see it is important to know the charge whether the ligand is neutral or any charge is present or not. Okay, it's important. So this, we know this is a carbonate ion, so it is -2 charge on it. This is 0, and bromine is -1. So on the complex, the entire complex will have +1. You assume this as X. So when you find out the X value, you'll get +3 here. Yes or no? And +3 here. This is the first thing. So you should be very comfortable with it. And how to find out the oxidation state. And for that, you should know the charge. I have given you all those examples. That is more than enough. Okay, fine. Now you tell me, what is the atomic number of cobalt?
27.
What? 27. Okay. So cobalt is 27 and its electronic configuration is argon 4s2 3d7. So for CO plus 3, the electronic configuration is argon. Why I am doing this? Not required basically electronic configuration, was fine, let it be. So basically we have 24 electrons, not required to write down this configuration. Here we have 24 electrons, right? Okay. So this wants to have 36 electron, the next higher configuration, right? So for 36 electron, it needs 12 more electron, right? 12 more electrons means its coordination number is 6 here, right? If you want to have 12 electrons, means there are 6 atoms which are donating electrons to the metal, which is cobalt here. So out of 6, you see, there are 4 NH3 molecules which are donating electrons to this cobalt. We know NH3 is monodentate ligand. So we can say all NH3 molecules are attached with cobalt. So out of 6, 4 coordination number has been fulfilled by NH3. Now 2 are left. So both the atoms, both the donor atoms in CO3 2-, CO3 2- carbonate ion is a bidentate ligand. But we have to see in the molecule, in the complex, how many atoms are donating electron. According to that, we can say that whether denticity of carbonate ion is 1 or 2, right? Maximum capacity is 2. It is bidentate ligand. 2 pair of electron it can donate. But what is the denticity in this compound? We need to check. Okay. So 4 electrons, 8 electrons are given by this 4 NH3 molecule. It requires 4 more. So all the 2 donor atoms in carbonate ion here will donate electrons to this cobalt. Hence, here in this complex, CO3 2- is a bidentate ligand. It's behaving as a bidentate ligand.
Sir,
But
excuse me, sir.
What?
Sir, why are we like, according to EAN, shouldn't we be taking a 27 as the atomic number? Why are we taking 24?
Because
Okay, it doesn't make a difference. Okay, okay.
oxidation state is +3, no?
Yes, sir. Yes, sir. Got it.
That's why I'm taking 24.
Yes,
Okay.
yes, sir.
Those
Yes,
examples, oxidation state is 0.
yes, sir. Understood, sir.
Yeah. So here you see, now here also the same thing. It requires 12 electrons, but out of 12, 5 NH3 is providing electron here. And this cobalt needs only 1 pair. So both carbon atom cannot, both oxygen atom in carbonate ion cannot donate electron to this cobalt. Cobalt does not require that much electron. So cobalt will say, okay, only 1 oxygen atom, I need only 1 pair, so give me only 1 pair of electron. Okay, so out of 2, only 1 oxygen donates electron to this cobalt. Hence, here in this molecule, this CO3 is behaving as a monodentate ligand. So it is bidentate in the first one and monodentate in the second one. So your answer is correct, Sana. Okay, 1 and 2 here. You can think of, so why not 4 NH3 donates and 2 donates from this side? That is not possible because NH3 is monodentate ligand, and if it is written here, it means it is bonded with the cobalt. So we have to consider all monodentate first, then we'll move into the polydentate ligands. So basically these two molecules, if I draw a rough diagram of it, the first one you see when we have 4NH3 molecule, we have cobalt here present. So cobalt somewhere here and 4NH3 like this, 1NH3 here, 1, then 2, then 3, and then 4 NH3 here, and carbonate ion is this. We have C double bond O, O minus, and both the carbonate ions are donating electron to the cobalt. So this is the structure we have. Denticity is 1, 2, 3, 4, 5, 6. 6 coordination number. Denticity is 2 for this, right, and 1 for all the ammonia. Now, what happens in the second one? Second one, we have the same thing, right? But there are 5 NH3. So, like I said, all monodentate you have to consider first. NH3, then we have NH3 here, and then we have NH3 here. And here we have one oxygen atom, O minus, carbon double bond O and O minus like this. Out of capacity is 2, it can donate 2 pair, but cobalt does not require 2 pair because already NH3 has given 10 electrons. It requires only 1. So only 1 oxygen donates. So here it is monodentate ligand, here it is bidentate. Did you understand this?
So what happens to the other oxygen?
It will be there as it is.
So then
Bond-
what will the charge
Carbonate.
won't be neutralized, no sir?
Sorry?
The charge won't be neutralized, no sir?
No, overall it will be neutral because there are electron, it donates electron, no. So overall it will be neutral because there will be some charge on cobalt also.
Okay.
Right, overall if you calculate. Yeah, so this is how the thing is, right? How the complex forms. And you see, I have given you the rough, a rough idea of it, how this is drawn. If I go a bit ahead, which we'll discuss a bit later, you see this here. If you look at this diagram, this structure, this structure looks like a square bipyramidal. Yes or no? Yes. Yeah. Hence, the structure of this molecule is square bipyramidal. That's what I was talking about. When it has to donate electron to the central metal atom, it will arrange itself in the 3-dimensional space, right? And hence, these are capable of showing, stereoisomerism if all the conditions are there. Correct? So this is the coordination number 6 compound, which is the most important one. We'll discuss this in stereoisomerism, and it is the octahedral complex. Okay, you can see the structure: 4 square cornered and 1 on the top, 1 on the bottom, octahedral complex. Same thing we have here also. Okay. Anyways, so this is flexidentate ligand. Okay. Next one, you write down chelating ligand.
Second one is also square bipyramidal, sir.
Both are the octahedral, square bipyramidal, the same thing.
Okay.
Write down chelating. Chelating ligand. See here, I'll just show you this structure. Chelation is a ring complex. Okay, like you see, you consider this one, 1, 2, 3. It forms a ring, right? Forms a ring. So this kind of ligand, which are capable of forming a ring like this, right, are called chelating ligand. Did you understand this? So for chelation, what kind of ligand we require? Polydentate or monodentate? Anybody?
Polydentate.
Polydentate, right? Because if it is monodentate, in case of NH3, chelation is not possible. Ring structure won't form. right? That's why all polydentate ligands are also considered as chelating ligands, okay? Because they are capable of forming a ring, cyclic ring, that we call it as chelates. The structure or the complex that we get by the polydentate ligands in which a cyclic structure is there is called chelates. Chelates are generally more stable than the normal complex because of cyclic structure, with only one exception. That exception I'll show you. First of all, you write down the definition into this. Chelating ligand, you write down all polydentate ligands. All polydentate ligands are chelating ligands. Are chelating ligands if on coordination, it results in the formation of it results in the formation of a closed cyclic ring. The formation of a closed cyclic ring. Next line, the complex forms in this way are called chelates. The complexes forms in this way are called chelates. And these chelates are more stable than the ordinary complex. And these chelates are more stable than the ordinary complex. Right? Chelates are more stable than the ordinary complex with only one exception. The exception is hydrazine. If the ligand is hydrazine, NH2, NH2, and both nitrogen donates electron to the metal, it forms a three-membered ring, and hence it is lesser stable. Yes, just a second, Aditya. All polydentate ligands are chelating ligands. If on coordination, it results in the formation of a closed or cyclic ring. The formation of a closed cyclic ring. The complexes forms in this way are called chelates, and these chelates are comparatively more stable than the ordinary complex.
Sir, other polydentate ligands that form a three-membered ring are stable, sir.
No. Three-membered ring is not stable. I'm just giving you an example. Right. It's not like because of hydrazine it is not stable. If three-membered rings are forming, then it is not stable in the normal.
Yes.
So the previous example also is not stable.
This is not three-membered in the previous one. This one. 4.
Okay, I don't see.
But yeah, if three-member ring is forming, then it is not stable. Right? I've just given you one example. Okay, this is one exception. Now the next one is ambidentate ligand. Ambidentate ligand, you must have, I must have discussed this in case of cyanide, the reaction of cyanide when we were doing in organic chemistry.
Sir?
Yeah.
So how is a ring more stable?
See, ring structure is generally more stable. Like the overall the surface area decreases, which enhances the stability of the molecule. Because of the ring structure, we don't have any other theory for this. We can say the surface area is less, and then see, actually what happens, these are complex compound. Complex in the term I'm using here in terms of, its structure and orientation in the space. Correct? So when the molecules, atoms are arranged in the space, right? So they always have to, they always wants to maintain the distance so that the overall repulsion has been minimized. It happens on its own. To minimize the repulsion only, like we have atoms, pair of electrons are there, bond pair electrons are there. So we have some random steric hindrance, lone pair repulsion, bond pair repulsion. So to minimize all this, the atoms, molecules are arranged themselves in the space in that way, right? So when the structure is a ring structure it is forming, so in that ring structure, the overall strain is very less, right? The distance is there, is maintained, overall strain is less. We have a certain angle where the strain has been decreased a lot. That's why we say that when cyclic structure forms, it has more stability. So there are multiple things. It's not like only one thing. You can talk about repulsion, you can talk about bond angle and other things, right? So all these factors overall, makes the structure, ring structure, more stable than the other or open chain complex that we get, right?
Yes, sir.
So in three-membered ring, the angle strain is dominates on all other things. The angle strain between the two bond pair of electrons is so high, and hence it is not stable. The basic thing that we have discussed so many times in organic chemistry, right? So ambidentate ligands are what? Write down the ligands which has more than one donor atom or sites. The ligands which has more than one donor atom or sites more than one donor atoms or sites available but while forming complex only one donor atoms only one donor atom is attached to the metal ion.
Sir, is attached to?
Sorry?
So could you repeat the last?
Your voice is breaking.
Sir, is attached to?
To metal ion. I'll repeat again, wait. The ligands which has more than one donor atom or sites available, but while forming complex, only one donor atom is attached to the metal ion at a time. It's not like all the donor atoms will attach. So like for example, you see cyanide ion. One second. One second, guys. Yes. Yes. So we were talking about ambidentate. So Cn minus, you see, the ligand is Cn minus, and when Cn minus is this, a carbon triple bond with nitrogen, one lone pair on nitrogen, carbon and a negative charge. Okay, two donor sites, carbon and nitrogen. If carbon donates, then it is known as cyno. If nitrogen donates, it is isocyano. Right? And cyanides, isocyanide forms, isocyanides in the minor product, right? Same thing we have if you take this one. I'll go to the next page, wait. N double bond O, O minus, nitrogen, just a second. Yeah, N double bond O, O minus, correct? So when nitrogen donates electron, nitrogen and oxygen both has the capacity to donate electron. We call it as nitrito N because nitrogen is donating electron. N double bond O, O minus, it is nitrito O. Okay, ambidentate ligand. We can talk about this SCN minus. This is thiocyanide. This is SCN minus when nitrogen donates. It is isothiocyanide. Basically, the first two are the most important one. Okay, one more I'll show you. Instead of sulfur, we have oxygen, OCN minus. So it is two more lone pair we have here. Here also. It is thiocyanide. It is cyanato O because oxygen is donating. If it is OCN, nitrogen is donating. It's lone pair. Then it is cyanato N. So all these are ambidentate ligand, more than one donor site.
So why can't these form polydentate ligands? So why can't these form?
See, actually, carbon nitrogen has triple bond, right? You will get it on your own. For polydentate ligand, the bond must be like this. No, there must be some angle between the bond. Then only it can rotate and donate, right? But since it is triple bond here, sp, so 180 bond angle must be maintained, right?
Yes, sir, yes.
That's why it is not possible. Little bit you think about it, you'll get it.
Yes.
Okay. So that's the thing. So these are ambidentate ligand. Okay. Now the next thing is Okay, next you write down coordination number. Coordination number. Coordination number, right? It is the number of atoms of ligand. It is the number of atoms of ligand that are directly bonded to number of atoms of ligand that are directly bonded to the central metal atom or ion by coordinate bond Okay, I'm repeating. Number of atoms of ligand that are directly bonded to the central metal atom or ion by coordination bond is known as the coordination number of that metal atom. Okay, coordination number is for metal atom. Coordination number of that metal atom. With example, you will understand this. Suppose if I take CO NH3 2 plus, right? So we have 4 nitrogen atom bonded with it. So coordination number is 4 here, simply. If you look at this example, if I take CO EN3 and 3 plus, what is the coordination number here?
6.
It is 6 because En is bidentate ligand and there are 3 ligands present, so it is 6. So if you write down the formula for coordination number, it is the number of ligands into its denticity. But you have to again cross check that how many atoms are bonded with, because the one that we have done, the bidentate and monodentate ligand, the carbonate for example, there if you use this form, you'll get it wrong. Okay, so those kind of understanding you must have while you are doing this kind of questions. Okay, so this is in general we use this formula. Let it be. This formula we use. Okay. If you look at the structure here, this one, how it is bounded, we have cobalt and we have En, right? So we have 2 atoms present here. Then I'll just write down, like this and this and this. 2 atoms will be like this, which is donating electron to the metal. Means one ligand is this, another ligand is this, and another ligand is this. Like this. Suppose these are the donor atoms here. It looks like fan, right? But actually, it is it is at the corner of the of the square bipyramidal. It's like that, like this. It is. Don't draw it. I'm just telling you. It is on the top bonded like this and this. So if you try to imagine this, imagine a square, right? Imagine a square, flat, not vertical. Flat square you imagine. In the center we have metal, and just to draw a line like this, straight line like this. Here the top we have 1 atom, and this corner, it is bonded like this. You have to imagine this a bit, then you can understand. And this kind of imagination is required when we do stereoisomerism over here, right? Center, you draw a line, flat square, right? Horizontal square. You draw a line, vertical line. Here you have one donor atom of the ligand, and another donor atom is at the corner of this square of the ligand. The line here, this point, this one donor atom of one ligand and another atom of the same ligand is here. And this is the ligand connected with each other. And these are donor atoms placed like this. Okay, this is COEN3. We'll discuss this also later on when we do stereochemistry in coordination compound. Mostly that part is the most important part we have here. Next, one more thing here is coordination sphere. Coordination sphere. Write down the definition. This, we also call it as coordination entity. Wait a second, let me just close the door. Okay, write down. The central metal atoms or ions and the ligands central metal atoms or ions and ligands are written within a square bracket which is called coordination sphere or entity. It is a single unit won't dissociate in the form of ions, won't dissociate in the form of ions, when dissolved in aqueous solution, and retains its identity. Done?
Yes.
Fine. So guys, we'll take a break now. We are done with it. We'll start with nomenclature in coordination compound after this. Okay. So we'll resume the session at 6:45. Nomenclature, the basic rules are same. You just need to focus a little bit on the nomenclature of ligands. How do we write down the name of ligands when it is neutral, acidic, or neutral, negatively charged, or positively charged? Okay, in that way, how do we write down the name? But the basic things are, the basic rules are same here. Okay, so we'll resume at 6:45. Take a break.